Hey, thanks a lot. Let's take a closer look at the picture that you guys drew. What a great picture. You definitely get the star for the day. When I talk to students across the nation, they draw the sun the same exact way. But our star is a sphere. It's an actual circle. As you can see, it is very circular, but at the same time, it is shaped like a ball, a sphere. If we were to hollow our star out, kind of like a fishbowl, it would take over 1.3 million tiny little Earths to fit inside of our star. Our star is so big that it would actually take over 110 Earths to line up across the whole diameter of the sun. Our star is very big, but it's actually a medium star compared to other stars. All the planets in our solar system revolve around our star. Have you ever thought about how many miles away the sun is from the planet Earth? Let's hear a few guesses. If you said 93 million miles, you're exactly right. If we were to try to travel to the star with an airplane from the Earth to the sun, it would actually take us over 26 years to travel to the sun. Speaking of travel, let's travel over to the Kennedy Space Center so we can talk to Rachel Power more about our magnificent sun. Rachel?
Thanks, David. I'm Rachel from Kennedy Space Center. And now that we have a little more information about the sun's size and shape, let's talk about the color. What color is sunlight? Many of you probably guessed some mixture of yellow, orange, and red. Those are the colors that are most easily detected by our eyes, but not really the color of sunlight. Is everybody sitting down? Because you might be surprised by this. The actual color of sunlight is this color. Yes, white light. But white light is a mixture of all the colors of visible light, the light that can be seen by the human eye. You probably already knew this. In fact, I want you to use your imaginations for a moment. You can close your eyes if you want. Imagine it's been raining outside, and the white light from the sun is shining down on Earth. Sometimes when that sunlight passes through the suspended rain droplets in the air, the water acts like a tiny prism, dispersing the light and reflecting it back to your eyes, and something beautiful appears in the sky. That's right, a rainbow. Rainbows are a circular arc of sunlight, so white light is a mixture of all the colors of the rainbow. So let's turn this simple white circle into a rainbow sun filled with all the colors of visible light. Do you remember all the colors in a rainbow? There are 7. Let's review them in order and add them to our sun. The first is red. So I'm going to color a sliver of my white light in red. And I'll draw a red R at the bottom of the paper. The next is orange. So, just like the red, I'm going to color a sliver of the white light in orange. And of course, don't forget the O. Next is yellow. So we'll add some yellow light to our sun. And now we have R, O, and Y. Roy. These are the first 3 colors of the rainbow. As I mentioned earlier, these are the colors of sunlight that pass through Earth's atmosphere and are detected by our eyes as the color of the sun, but they're not the only colors in sunlight. Roy has a middle initial of G, and the G stands for green. So this means there is green light in our sun as well. So white light is also green. The next color is often thought of as the color of our sky. But really what you are seeing is the blue light from the sun scattering off all the tiny air molecules on a clear sunny day. Now I want you to notice that as I add the blue, I'm going to be very gentle. I don't want to press down very hard because I want it to be a nice light shade of blue. Now we'll start on Roy's last name, which starts with the letter B. How many of you remember the next color? It's one of the most difficult to remember, so I'll give you a clue. It starts with the letter I. Indigo. Now, indigo is a deep blue, which historically came from the natural dye obtained from the indigo plant. It was used mainly for the color in blue jeans. And my box of crayons did not come with indigo. So I'm going to use the same blue crayon. But this time I will press harder, making a darker shade of blue. And this will be my indigo. The final color of the rainbow is a bluish purple called violet. I will fill up the remaining white light with violet. Now we have Roy G. Biv, which helps me remember the 7 colors of the rainbow in order: red, orange, yellow, green, blue, indigo, and violet. And when the sun is low on the horizon, like at sunrise or sunset, any of these colors might reflect off the air and clouds in the sky. So the sky is not always blue. In addition to the colors of visible light, the sun's energy includes light that is not visible to our eyes. That's why we use technology to help us study the sun. SDO has 3 instruments on board, including a set of 4 telescopes with different filters to provide 8 full sun images every 10 seconds, 24 hours a day, 7 days a week. That's a lot of pictures. These instruments help us learn more about the sun's energy, including the heat, or infrared, visible light, or Roy G. Biv, and ultraviolet, or UV light, which we cannot see, but it can be harmful to our skin. This is why you should wear sunscreen when you are exposed to the sun. I bet you'd like to learn more about what SDO can see with those 3 instruments. So I'm going to hand this over to Erin so you can learn even more about our magnificent sun.
These look fantastic. I am so excited to help add more facts to your perfect pictures of the sun. Just 1 second. Rachel is exactly right. We can learn a lot of great information about the sun with the help of our friend SDO. Let's take a closer look at the sun to see just how dynamic a star it truly is. I'm sure you all saw these spots earlier. Now, these are just not spots, my friends, but these are areas of lots and lots of energy, and they have a very special name. Repeat after me: sunspots. Very good. Sunspots are areas of lots of energy on the sun that begin to swirl around itself, and that energy builds up and up and up, and as it continues to build up, the temperature drops. That is why sunspots look darker than the rest of the surface of the sun, because they are actually cooler than the rest of the sun. On average, the surface of the sun can range between 10,000 to 1 million degrees Fahrenheit, so sunspots are cooler than that. Now, after a while, sunspots cannot hold all of their energy, so they burst open. And this makes our scientists here at NASA very excited because we can see these reactions, all different kinds, with the help of our friend SDO. Sometimes we can have a big flash of light we call a solar flare. Other times we can have a big loop come off the sun, which we call prominence, or the largest of all these explosions we call the coronal mass ejection, or CME, which is just that, a huge explosion that pushes out pieces of the sun into space. Now, all of these reactions affect our solar system a lot like how weather affects us here on Earth. That's right, just like we have Earth weather, we also have solar weather. Whenever we see reactions such as CMEs, it pushes out pieces of the sun that we call solar wind. Little SDO wants to come in and share with us an up-close and personal view of these reactions. Thank you so much, SDO. So here we are at the sun. We just had a sunspot burst. That big flash of light was a solar flare. And in 3, 2, 1, there, my friends, is our coronal mass ejection, or CME, pushing out solar wind, or pieces of the sun, into space. Now, we are very fortunate because around planet Earth, we are protected by what you see right here. We call this a magnetic field. So when the solar wind comes whooshing by, we on the surface are safe. But the solar wind and the magnetic field around our planet Earth react with one another. We can see these reactions at the northern and southern pole regions as this, a beautiful display of dancing lights in the sky. In our half of the world, we call this the northern lights, or the aurora borealis. Beautiful display of dancing lights. My friend Lyle is going to share with us a little bit more information about solar wind and auroras in just a few moments. But before we do that, we need to add some sunspots to our perfect picture. So please take out either a brown, a black, or a gray color. Hold it high in the sky. Thank you very much. We are going to add 3 sunspots to our perfect picture to show how sunspots can pop up on the surface of the sun. So, taking my brown right here, I'm going to add 1, 2, and 3. You may add your sunspots any place, any size. Go ahead and do that for me right now, please. Wonderful. Let's take a closer look at this. Boys and girls, your pictures all look fabulous. And now, like I said, we're going to pass you off to Lyle, who's going to share with you a little bit more information about solar wind and auroras. So there you go, Lyle.
Thanks, Aaron. Wow, these look great. I'm excited to add to our picture soon. I'll put it right over here for now. Aaron's right. Things like flares, prominences, and coronal mass ejections blow little pieces of the sun out into space. Let's take a look at a flare and a prominence doing just that. Here's a solar flare, and you can see it getting ready to blast material out into space, and it happened to be pointed right at one of our satellites. Pretty amazing. Now, let's take a look at a prominence. This prominence is getting ready to, again, blast some material out into space in a very large explosion. And here it goes. That is so amazing. Those little pieces of the sun are so small we can't see them with our eyes. But our satellites studying the sun can. Let's look at a video of the sun blasting the solar wind out into space. Here you can see those little tiny pieces getting blasted out into space towards Earth and all of the other planets, and in all directions. Aaron showed you how the solar wind travels through space and reaches Earth and creates those auroras. We also saw what those auroras look like from the ground. Now imagine being able to see those auroras from space. How many of you would like to be astronauts when you grow up? Raise your hand. Okay. Well, I want to show you something that may change the minds of those of you who didn't raise your hand. Let's take a look. Here you can see the auroras in a picture taken by astronauts on the space shuttle. Pretty impressive. Now here is what the auroras would look like if you were an astronaut orbiting Earth on the International Space Station. Now, if it meant getting to see the auroras like that, how many of you think you might want to be astronauts now? A few more of you? All right. Well, now it's time to add something to our picture. So let's take a look at our picture over here, and we are going to add the solar wind to our drawing. Since the solar wind is so small that we can't see it with our own eyes, we can use our imagination and pick whatever color we want. I'm going to pick green. We're going to just draw some dotted lines coming off of the sun like this. And when we do that, we're going to make them go all the way out, because these solar wind particles, they will travel all the way to Earth and even beyond the planets. Let's take a look at this now. Now that we've drawn the solar wind, we have a beautiful picture of the sun that shows its round shape, its rainbow of colors, its sunspots, and the solar wind that blows throughout the solar system. We've really learned a lot today. Well, thank you so much for your time. From all of us at NASA, bye-bye.